Here's something a little strange. You take last night's dinner, cold from the fridge, and you put it in a box. You press one button. 30 seconds later, the food is steaming hot. But the plate underneath is barely warm, and the air inside never caught fire. No flame, no glowing coil. Nothing you could actually see happened in there. So how did the heat get inside your food? To figure that out, we're going to follow one invisible wave. From a humming engine buried in the wall of that box, all the way down to a single molecule of water. Grab a marker. Let's draw it. Start with the name, because the name is doing a lot of lying. A microwave isn't some exotic death ray. It's the exact same stuff as visible light, the radio in your car, and the warmth you feel standing in the sun. All of it is electromagnetic waves. The only thing that changes between them is how stretched out the wave is. Radio waves are long and lazy. Visible light is tiny and tight. Microwaves sit somewhere in the middle, and the ones in your kitchen flip back and forth about 2.5 billion times every single second. A frequency of 2.45 gigahertz. Hang on to that number. That rhythm is the entire secret of this video. Now meet the real hero of the story, the humble water molecule. Almost everything you eat is soaked in the stuff. And water has a weirdly specific shape. One oxygen atom, two hydrogen atoms, bent like a little boomerang. Because of that bend, the molecule comes out lopsided. The oxygen end is greedy. It hogs the electrons and goes slightly negative, which leaves the two hydrogens slightly positive. So every single water molecule is a tiny bar of electric charge. Scientists call it a dipole, a plus end and a minus end. And here's the part to remember. Just like a compass needle, the moment something tugs on it, it wants to spin around and line up. Keep that in your back pocket, because we are about to start tugging. This is where the heat actually comes from, so stay with me. A microwave is really just a moving electric field. Picture an invisible force that points one way, then snaps around and points the other way, over and over. The instant that field switches on, our little water molecule whips around to line up with it. But the field refuses to hold still. It flips. So the molecule flips to chase it. It flips again. The molecule scrambles to keep up. Now bring back our number. This field reverses billions of times a second. So every water molecule in your food is getting twisted back and forth billions of times a second, frantically trying to stay lined up with a field that keeps yanking out from under it. And here's the payoff. These molecules are jammed in shoulder to shoulder. Every time one twists and lurches, it shoves and grinds against its neighbors. That grinding, that molecular friction, that is heat. Because temperature is really nothing more than how fast molecules are jiggling. The microwave doesn't pour hotness into your food. It grabs billions of water molecules and shakes them, and all that shaking is the warmth. The food, quite literally, heats itself, from the inside, molecule by molecule. Now, you've probably heard a story that goes like this. Microwaves work by hitting the resonant frequency of water, like an opera singer shattering a wine glass with one perfect note. It's a great story. It's also wrong, and it's worth fixing. Water has no magic shattering note at 2.45 gigahertz. In fact, here's the clever part. If engineers had tuned the oven to water's strongest absorption, the energy would get devoured by the very first layer of food and never reach the middle. You'd get a scorched surface wrapped around a frozen center. The frequency we actually use is deliberately gentler, picked so the waves can sink in a little before they hand over their energy. It's not one wine glass shattering. It's a whole stadium crowd shaking. Billions of tiny nudges, not one perfect note. So where do these waves even come from? Behind the wall of the oven sits the engine, a gadget called a magnetron. It's a surprisingly clever little vacuum tube. At its center is a hot filament that boils off a cloud of electrons. Around that sits a ring of metal, carved with hollow, scooped-out cavities. Normally those electrons would just rush straight out to the ring. But a powerful magnet bends their path, forcing them to spiral instead. And as that swirling cloud of electrons sweeps past the open mouths of the cavities, it sets them ringing. The same way blowing across the top of a bottle makes a tone. Those cavities are sized, so they ring at exactly 2.45 gigahertz. That ringing is your microwave. A little antenna taps it off and sends it on its way. And here's the kicker. This one component is the entire reason microwaves shrank from room-sized military hardware down to a box on your kitchen counter. From the magnetron, the waves shoot down a metal tunnel called a waveguide and spill into the cooking chamber. Now the oven has exactly one job. Keep those waves trapped in there with the food and out of your kitchen. The whole box is a metal cage, and microwaves bounce off metal like light off a mirror, so they ricochet around inside, blasting through the food again and again. But hang on. What about the door, the part you stare through? Look closely and you'll spot the trick. A mesh of tiny holes. Microwaves are about 12 centimeters across. Way too fat to squeeze through those little gaps, so they stay locked inside. Visible light, which is thousands of times smaller, slips straight through. That, right there, is why you get to watch your dinner spin without getting cooked along with it. But all that bouncing creates a problem. When the waves ricochet off the metal walls and cross back over themselves, they overlap. In some spots, they stack up and reinforce each other. Those become intense hot spots. In others, they cancel out completely. Those become cold spots, where almost nothing happens. The result is an invisible, frozen pattern of hot and cold zones, standing dead still inside your oven. If your food just sat there, it would cook in stripes. Scorching here, icy there. And that, finally, is what the turntable is for. By slowly spinning, it drags every part of your meal through the hot zones and the cold zones in turn, evening the whole thing out. Some ovens skip the turntable and instead hide a spinning metal paddle up top that stirs the wave pattern around the room. Either way, the goal is identical. Never let the food sit still in an uneven field. Here's one thing even the turntable can't save you from. Microwaves don't actually reach the dead center of a thick piece of food. They only push in about an inch before they've given up all their energy. So the outer layers heat directly, and the very middle just has to wait for that warmth to crawl inward the slow, old-fashioned way. Conduction. One molecule handing heat to the next. That's why a big frozen burrito comes out lava hot at the edges and still an ice cube in the core. It's also why letting it rest for a minute after the beep genuinely works. You're giving the heat time to even itself out. And it's why the instructions always tell you to stir halfway. They're not being annoying. They're being physicists. A few last mysteries, knocked out quick. Why does metal spark? Those bouncing waves shove electrons through the metal, and at a sharp edge, a forked tine, a strip of foil, the charge piles up until it leaps through the air as a spark. Why does a grape explode? Two grape halves act like little antennas, funneling the energy into the thin bridge between them until it bursts into plasma. Why does the plate stay cooler than the food? Glass and ceramic hold basically no free water for the field to grab, so the waves sail right through. Your plate only warms up by touching the hot food sitting on it. And the air? Dry air has nothing to grab either, which is why the inside never feels like an oven. The microwave is astonishingly picky. It ignores the plate, ignores the air, and goes straight for the water. So let's trace the whole journey one more time. A magnetron rings out invisible waves, 2.5 billion beats a second. They flood a metal box and grab the water molecules in your food, whipping them back and forth until their own friction turns into heat. A turntable spins to spread that heat around, and slowly it creeps inward toward the core. No flame, no coil, just an invisible rhythm, shaking your dinner warm from the inside out. Not bad for a box that lives in the corner of your kitchen. So next time you're standing there watching the plate go round, you'll know exactly what that hum is really doing. If you've got a machine in your house you've always wondered about, tell me down in the comments. Because there's a hidden world of physics inside everything you own. And we are just getting started.